Hi there, this is Professor Shannon Gracey from Costa College. Today we're going to be covering 2.2 from the Larson and Edwards Calculus text. And this section is called Basic Differentiation Rules and Rates of Change. So last time you learned the quote-unquote hard way to find the derivative function. Now we're going to learn some shortcut rules, and so usually people are pretty happy with this section. Some key things to remember are algebra, and trig identities. Those kinds of things can help. So let's go ahead and get started by warming up. We'll use the limit definition in the warm-up, and then we will start learning the new stuff. All right? On your mark, get set, go! Warm it on up. Alrighty, let's see how you did. So this guy, the first one, sometimes I think of it as so easy, it's hard. So let's get started. We know that f prime at x is equal to the limit as, whoops, move this over, as delta x approaches 0 of our function. Let's write it out at the top. Remember, the general rule for f prime at x was the limit as delta x approaches 0 of f at x plus delta x minus f at x all over delta x. Cool so far? So now this guy, what do you have the graph of here for f at x? Good, it's a horizontal line, right? At y is 2. So it doesn't matter what you plug in there, what are you going to get for f at x plus delta x? Awesome. You're going to get 2. For f at x, you get 2, right? So we'll end up with 2 minus 2 over delta x. Notice that we are not using direct substitution at this point. What is 2 minus 2? Good, it is 0. And 0 divided by anything other than 0 is great, 0. So now we no longer have a delta x to worry about, and we're just evaluating the limit of a constant, which is beautiful, the constant. So f prime at x is just equal to 0. And that makes sense, right? Because the slope of a horizontal line is great, 0. Okay, so next up, we'll have f prime at x is equal to the limit as delta x approaches 0 of, what is our f of x plus delta x? Good, x plus delta x, the quantity squared, sorry, the dogs are out, or in, minus f at x, which is x squared, all over, great, delta x. So this gives us that f prime at x is the limit as delta x approaches 0 of, good, x squared plus 2x times delta x plus delta x squared minus x squared all over delta x. And we'll get f prime of x equals the limit as delta x approaches 0 of, do you see that the x squareds 0 out? And then we'll be able to factor out a factor of delta x, and we'll be left with 2x plus delta x all over delta x. Delta x divides out to be 1. And using some direct substitution, we're going to get, beautiful, now we're on direct sub, we'll get 2x plus 0. So the thing we're directly substituting is delta x going to 0. And at the end of the day, we get, great, 2x. So let's just kind of check out a couple of things. What did you notice about this one here in particular? We started out with x squared. So f of x equals x squared has a degree of, great, 2. And we went down to a degree of 1. So keep that in your mind when we learn about that power rule. Okay, to this guy over here, we've got f prime of x is equal to the limit as delta x approaches 0 of, good, cosine at x plus delta x minus cosine at x all over, actually, delta x. Good so far? Now we're going to need to use some tricks here. The first trick is what? Beautiful. Cosine at a plus b is going to be equal to, great, cosine a times cosine at b minus sine at a times sine at b. And what else do you think we might use? Well, let's just go with this guy, and then we'll figure out the other stuff. So now what do we have? F prime of x equals the limit as delta x approaches 0 of, good, our a is x and our b is delta x. So we'll have cosine at x times cosine at delta x minus sine at x times sine at delta x. And then we still have this minus cosine at x hanging out. And that's all over delta x. Okay, so let's just, this guy here is equivalent to all of this. Groovy? Awesome. So, continuing, we'll have, now, this is where we're going to need some other cool math stuff. What were those special trig limits? Great. Recall that the limit as, let's use theta, approaches 0 of sine at theta over theta equals what? Perfect, 1. And the limit as theta approaches 0 of, great, 1 minus cosine theta over theta equals 0. So we're going to be using that stuff in conjunction with some algebra now. So here we go. F prime of x will be the limit as delta x approaches 0 of. Now, do you see we have 3 terms in the numerator. And do you see that the first and the third term, there's my little hand here, the first term here and the third term here have a factor of cosine at x. So I'm actually going to factor out a negative cosine at x, and that will give me 1 minus cosine at delta x all over delta x. So basically, all of this stuff here is equivalent to this, okay? And then continuing, we will have, let's extend our equal sign, and I'm going to move this more to the middle. We will have minus sine at x times sine at delta x. Good so far? Okay, so putting this in the format that we need, or getting there, we'll have the limit as delta x approaches 0. Now recall that the limit of a difference is the difference of the limits, okay? So we'll have negative cosine at x times 1 minus cosine at delta x all over delta x, and then minus the limit as delta x approaches 0 of sine at x times sine at delta x over delta x. Okay, so far? Perfect. And the factors that just have an x in them are not affected by sending delta x to 0. So we can actually pull them out of the limit. So we'll end up with negative cosine at x times the limit as delta x approaches 0 of 1 minus cosine at delta x over delta x minus sine at x times the limit as delta x approaches 0 of sine at delta x over delta x. Good so far? Awesome. So at the end of the day, f prime of x, well, almost the end of the day, we'll get negative cosine at x times, good, 0, minus sine at x times 1. Awesome. And so by the special trig limits, we got, for this guy, we got 0. And for, I don't know, for this one here, we got 1. So we'll end up with f prime of x is equal to negative sine at x, and you're done. Great. How'd you do? Awesome. All right, so here we go on to the constant rule. So here, basically, this is saying the derivative with respect to x of a constant is equal to 0. So basically, isn't this theorem the equivalent of saying that the slope, because remember derivative is slope, of a horizontal line is 0? Right? And we actually use the limit definition on finding the derivative of the constant 2 in the first example. So here, what will we get? If we have g of x is equal to 6, and if we apply the derivative with respect to x to both sides, what will happen is we will get the derivative with respect to x of g of x will be perfect, g prime of x, and on the right side we'll get 0. So there's your first shortcut. You like that better? Okay. Now, the power rule. There is a proof of the power rule in your book. We'll do some proofs as we go along today, but I don't find that this one is going to be really will help you understand the formula better. So we'll skip the proof. So this guy's basically saying, as we talked about in part B of the warm-up, are the degree when we evaluate the derivative of a function, the degree seems to be decreasing by 1. So notice that we end up with this formula here. When you're differentiating with respect to x to the n, you multiply by the derivative or by the power, and then you reduce the degree of x by 1. Okay, so here we go. We've got our f at x is equal to x to the 5th. So now I'm applying this derivative. I can't talk today, sorry. The derivative is a linear operator, so you can apply it to both sides of the equation. So what do I get on the left side? Beautiful, f prime of x. Now on the right side, we'll exactly get, good, that 5 moves to the front. And then we have times x to the 5, and then the other part of the, applying the derivative formula is decreasing it by 1. So at the end of the day, what will we get? Great, f prime of x is equal to 5x to the 4th. Good so far? Awesome. All right, you try the next one and see how you do. So go ahead and pause the movie and see how you do. Okay, so we're starting out with f at x is equal to x to the 1/2. Applying the derivative with respect to x on both sides, we will have on the left, perfect, f prime at x, and on the right side, what happens? Great, we'll get 1/2 times our something to the, so our something is x to the 1/2 and then minus 1. So now f prime of x is equal to, good, 1/2 times x to the negative 1/2. Now what we end up doing often is this. I know it might seem kind of silly with a problem like this, but we're going to be needing to find the zeros of the derivative. So the best thing is to make it one happy fraction. Your derivative function should be one happy fraction without any negative exponents. So basically a simplified rational expression. So we will have, for this one, f prime of x is equal to 1 over 2x to the 1/2. Or if you want to write that in, actually no, we don't need to write it in radical notation because it was given as a rational exponent. Good so far? Great. Let's see how we did on the next one, and feel free at any time to pause the movie and try it out yourself. So we have this f at x is equal to x to the negative 5/3. Applying the derivative with respect to x at both sides, we get f prime of x equals, good, negative 5/3 times x to the negative 5/3 minus 1. Right, so be careful on these. And I really recommend that you write out this whole thing for your first few problems in the homework because it really helps you to remember the rule. So we'll have f prime at x is equal to negative 5/3 x to the negative, good, 8/3. And writing it with positive exponents, we will have negative 5 over, actually, let's pretty it up. We'll have negative 5 over 3x to the 8/3. Okay, so next up, we've got the constant multiple rule. So it turns out when you're differentiating, the derivative with respect to x of a constant times a function of x is equivalent to the constant times the derivative with respect to x of f at x. So let's show the proof of this guy using our limit definition. So what we'll have is f prime of x equals the limit as delta x approaches 0 of our constant times f at x plus delta x minus our constant times f at x all over delta x. Good so far? This will give us, do you see where you can factor out a c? So we'll have the limit as delta x approaches 0 of c times f at x plus delta x minus f at x all over delta x. But recall that you're allowed to bring a constant factor or a scalar that's inside a limit to the outside of the limit. So we'll have c times the limit as delta x approaches 0 of f at x plus delta x minus f at x all over delta x. But what is that? Perfect. That is f prime of x. So we just did our first math proof. How do you feel? So here, all of this stuff here is this. Okay? All right. So now let's check out the next problem. Find the slope of the graph at f of x equal to x third to the third at these values. So what might we want to do first? Beautiful. Find the slope of the graph in general and then evaluate the derivative function at each of the values below. So if we rewrite f at x is equal to 2x to the third, differentiate both sides with respect to x, and then we'll have f prime at x equals, using our constant multiple rule, do you see this is 2 times the derivative with respect to x of x cubed, okay? And then we'll have f prime of x is equal to 2 times, so applying our derivative, we'll have 3 times x to the 3 minus 1, which will give us f prime of x is equal to 6x squared. How'd you guys do? Awesome. So finishing the problem, what do we have? For x equal to 2, we need to find f prime at 2, which is equal to 6 times 2 squared. So f prime at 2 is, great, 24. And over here, we'll have f prime at negative 6, and that's equal to, good, 6 times negative 6, the quantity squared. So f prime at negative 6 is equal to, I think that's going to be 216. Does that look okay? Good. And then lastly, f prime at 0 will be 6 times 0 squared. So f prime at 0 is 0. Alrighty. So now, and it's, it's good to take a look at what's going on with a picture. I didn't leave that much room, but that's okay. We'll check it out. So we have our original function was 2x cubed. And then let's go ahead and graph our derivative functions. So let's see, we went into, remember, great, math. And then n derivative is 8. We're doing it with respect to x. Our function is 2x. Actually, well, let's try it out. Our function is, no, you know what? Let's just do like we had done before. We had put our y1 in there. So we'll go to vars, and we want y vars. We're dealing with functions, and we put that in our y1. And then we're going to look at x equal to x, and we'll go ahead and go on our standard zoom. Well, no, actually, let's do, well, we can start with zoom standard, but I think we're going to need it to be higher for some of our other stuff. So that's kind of our general graph. Let's go to the window because we were interested in high values, remember, and low values. So negative 216 has to be in there. So so for our y, let's do for our y min, we'll do negative 250. And then we can have our y max go ahead and be, I don't know, 30. And then the scale for the y we can have be 10. And let's see what that looks like. Oh, that's right. We got a positive value. We're going to switch the window for the y. My bad. So here we go. Our y min we could do at the negative 30. And our y max we want to be 250. All right. Let's graph this guy. And then, we can go ahead and do, second calculate value. So what did we have? I think one of them was when x was negative 6. Do you see that we're looking here at y1? But what about if we go to y2? Do you see we get our value there? So I'll go ahead and copy that one. Make it smaller. I know it ends up being real small, but you'll see that that here the graph itself, do you see it's always increasing, and so the derivative is always positive except for right at x is 0 where you have a 0 slope. All right, so anyway, that's a picture of the two, and let's kind of move on. All right, so we've got next up we've got the sum and difference rules. So I'll go ahead and do the proof for just the positive. The difference works similarly, but it turns out that the derivative of a sum or difference of functions is the sum or difference of the derivatives. So we'll have the limit as delta x approaches 0 of f at x plus delta x. And by the way, we're doing d dx of f of x. Okay, so the sum and difference, we got shit going on too. Okay, so why don't we let h equal to h of x equal to f of x plus g of x. So h prime of x is equal to the limit as delta x approaches 0 of f at x plus delta x plus g at x plus delta x minus f at x plus g at x all over delta x. Good so far? All right, so now h prime of x will be equal to the limit as delta x approaches 0 of, we can commute the terms. So do you see we'll have f at x plus delta x minus f at x, I'm putting the f's together, plus g at x plus delta x minus g at x. And this is all over delta x. And we know that the limit of a sum is the sum of the limits. So we get h prime of x equals the limit as delta x approaches 0 of f at x plus delta x minus f at x over delta x plus the limit as delta x approaches 0 of g at x plus delta x minus g at x all over delta x. But what are those two limits? Good. That's just f prime of x plus g prime of x. And so we're all done. What do you think? Awesome, right? Okay, so here we go. Now let's go ahead and find the equation of the line tangent to the graph of f at x equals x minus the square root of x at x equals 4. So what should we do first, do you think? Good. Find the slope at x is 4. Okay. So there's other ways you could start too, but that's a good starting point. So what is slope? Slope is derivative. Good. And derivative is slope. Good. So now let's go ahead and rewrite f, because notice that we've got a radical there. So we might want to switch that to great rational exponents. So f at x is equal to, let's write this as x to the 1 minus x to the, good, 1/2. And so now applying the derivative with respect to x to both sides, what will happen is we'll get great f prime of x, and then using that rule we just learned, we know that we've got the derivative with respect to x of our x to the 1 power, and then minus the derivative with respect to x of our x to the 1/2 power. So I just applied the rule that we proved last time. So now, using the power rule, we'll have, so x to the 1 is going to give us 1 times x to the 1 minus 1. Good so far? And then minus 1/2 times x to the 1/2 minus 1. So we'll have f prime of x is x to the 0 minus 1/2 x to the negative 1/2, which will give us f prime of x is 1 minus 1 over 2x to the positive 1/2. Now, since we were given a specific value of x, we can just stop simplifying there. If you want to, if it helps, you can find, you can rewrite it in radical notation. So f prime of x will be 1 minus 1 over 2 root x. So f prime at 4 is equal to 1 minus 1 over 2 times root 4. So I just plugged in 4 wherever I saw an x in the derivative function. And so what will I get? Good. That'll be 1 minus 1/4, which is 3/4. Okay, so far? Perfect. So what else are we going to need? I mean, sometimes it's useful, just to figure out all the pieces you're going to need. So if you went over here, we'd want to write the equation of the line tangent to our function f at x is 4, right? So basically, remember that you're going to have y minus y1 is the slope times x minus x1, but the slope will be the derivative. Now what's missing? What's my x1? Good, 4. But I don't have my y1, do I? So that tells me over here I need to find what the heck f at 4 is. So f at 4 is 4 minus root 4. So now I'm evaluating the original function at x is 4, so I can get the corresponding y value. So f at 4 is 4 minus 2, which is 2. Now I have all my pieces. So I'm going to have y minus 2 is the slope, which was 3/4 times x minus 4. So this is everything that, all the pieces here. So our slope we found to be 3/4, right? And our x value was given as 4 in the problem. Our y value we found to be 2 when x is 4. And so there it all is. How you feeling? Awesome. Okay, we did it. All right, so derivatives of the sine and cosine function. I showed you the proof for the second one over here. And it turns out the derivative with respect to x of sine at x is cosine at x. So now we don't need to use our limit definition. So let's just go ahead and take a look at what we have. So f at x here, couldn't we write this as 1/6, which is a scalar, times sine at x? Good. And so when we differentiate both sides with respect to x, on the left we'll get, good, f prime of x, and on the right, remember you can bring out that scalar, and then you're going to evaluate the derivative with respect to x of sine at x. So f prime of x will be 1/6 times, good, cosine at x, and you're done. So this here had an output of this. Are we good? Beautiful. So why don't you guys try the next one? Notice that your independent variable is now theta. So instead of evaluating d dx to both sides, what would you do? Good. Evaluate d d theta. All right, let's see how you did. So now I'll just rewrite it so we've got more space. R at theta is 5 theta minus 3 times cosine at theta. D d theta, applying d d theta to both sides, we will have, great, r prime at theta is equal to, so now we're going to apply that the derivative of a difference is the difference of the derivatives. So we'll have d d theta of 5 theta, I'm going to write it to the 1 power, and then minus d d theta of 3 times cosine theta. Now, r prime at theta will be equal to, so remember that constant rule, the scalar multiple rule, so we can write this as 5 times d d theta of theta to the 1 power minus 3 times d d theta of cosine at theta. So we'll get r prime at theta is 5 times, good, 1 times theta to the 1 minus 1, and then minus 3 times, good, we'll have negative sine theta. So here we have d theta here has an output of negative sine theta. And then we'll have d theta of theta to the 1 is this guy, using that power rule. So let's see, we'll have r prime at theta is 5. Remember, that's going to be 1 plus 3 sine theta. And we're all set. How'd you do? Awesome. So now let's look at a little bit of some application for derivatives. We'll get into a lot more in chapter 3, but now we can look at some different things about rates of change. So we've seen how the derivative is used to determine, good, slope. Now, oops. The derivative may also be used to determine the rate of change of one variable with respect to the other, and I've been using that language a lot already. A common use for rate of change is to describe motion of an object moving in a straight line. So in these kinds of problems, you know, what's going to happen is you're going to use a horizontal or a vertical line. So basically, movement to the right on a horizontal or up is considered to be in the positive direction, and moving to the left or downwards is considered to be in the negative direction. Okay, I'll put upwards. All right, so the position function is denoted by S, and it gives the position relative to the origin of an object as a function of time. So if over a period of time, delta t, the object changes its position by delta s is equal to s at t plus delta t minus s at t, then by this familiar formula, rate is distance over time, the average velocity is going to be your change in distance over change, sorry, forgetting an E, in time. So let's check this out. Isn't that going to be slope, right? So to make it instantaneous, we need to do the derivative. So here, let's check out this problem. We've got a ball being thrown straight down from the top of a 220-foot building with an initial velocity of negative 22 feet per second. The general position function for free-falling objects in feet is s at t is negative 16t squared plus the initial velocity times t plus the initial position. So basically, what have we been given? Good. We've been given that the initial velocity is negative 22 and the initial height, right, or the initial position is S0, which is 220 feet. Okay, so far? So let's take a look. S at t, using that information, is equal to negative 16t squared minus 22t plus 220. So what is the velocity going to be after, or how can we find the velocity? Great. The velocity is the derivative with respect to t of our position function. So this is going to be s prime at t is equal to, so I'm going to go a little bit faster, negative 16 times dt of t squared. So I'm kind of moving that scalar out of the derivative as I bring the derivative into each term, minus 22 times the derivative with respect to t of, remember that's like a t to the 1, and then plus the derivative with respect to t of this constant 220. Okay, so far? Beautiful. So s prime at t is negative 16 times, good, 2 times t to the 2 minus 1, using that power rule, minus 22 times 1 times t to the 1 minus 1. And then what's the derivative of a constant? Beautiful. 0. So we'll get 0 for this last one. So now s prime at t, simplifying, will be good. Negative 32t minus 22. Good so far? So what's left to do for this problem? Good. So s prime at 3 is equal to negative 32 times 3 minus 22. So s prime at 3 will be negative 96 minus 22. And all I did here is I plugged in 3 wherever there was a t in the derivative function, right? Which is, by the way, velocity. So let's make that clear. So the v at t is this. You know what? I'm going to do this. Equals v at t. So v at 3 is that, and we'll have v at 3 is this. So v at 3 will be negative 118, and it's going to be in feet per second. Good so far? Awesome. Okay. So now let's see what we have to do on this next guy. We want to find the velocity after falling 108 feet. So what all do we need here? What do you think? We have the velocity function. Good. So remember the velocity function was v at t is negative 32t minus 22. So that's what we got. But do we know what to put in for t? Good. No, we don't. So remember that our general position function was s at t is equal to negative 16t squared minus 22t plus 220. Now, after we fall 108 feet, what do you think is going to happen? Where are we going to be? Well, let's check it out. 220 minus 108 is going to be our S0. Or no, our S at t, right? Our S at t. Which is equal to 112. Good so far? So, setting this up, we'll have 112 equals negative 16t squared minus 22t plus 220. And then we will have, good, we will have 0 equals negative 16t squared minus 22t, and then we'll end up at 108 plus 108. And factoring out, I think we can factor out, or actually instead of factoring, why don't we just divide both sides by 2, because, and we got to do each term here, so we can divide out a 2. And actually, let's just divide out a negative 2, make it prettier. So we'll get 0 is 8t squared plus 11t minus 54. Okay, so let's just go ahead and use our graphing calculator to solve this guy. So that way we could see a picture of it too. So let's go to our y equals, and then let's see what we've got. So we'll have what we have now is we have, let me just clear this guy. I'm going to go ahead and use X's. It's just easier because that symbol's here, but we'll put T's on the paper. So here we've got 8 T or X squared, and then we've got plus 11 X minus 54. All right, and we're gonna go ahead and we're gonna turn this off right now because we're not finding the derivative of that. We already have our derivative function. We'll come back, but what we do want to find are the zeros. So let's go ahead and let's go ahead and find the zeros. And I don't know where we're going to be, so I'm just going to go start with zoom standard. See what happens. Okay, so we can zoom out, but do you see that we're crossing the line, the x-axis here, and we're not interested in negative time, so we can zoom it out a little bit, but we pretty much already have what we need. So zoom out is 3. Well, that's not very illuminating. So what's our window here? We certainly, let's see, what was the graph? Okay. So we don't need this guy to be so, well, you know what? We'll just change the scale, I guess, to 10 here. And we'll do the same for the y's. Maybe get a prettier picture. And of course we're going to need to make the minimum negative for this y. Yes, it's yelling at me now. Window. I think we're good. Okay, so let's go ahead and graph. And the x's, we don't need them to be so big. So coming back, adjusting a little more. Why don't we just keep x from negative 10 to 10. And we can change this back to 1. And let's see if that looks prettier. There we go. Finally. All right, so now if we go to second, calculate, I'm going to find the zeros. Left bound, that's good. Right bound, we want to get above the axis here. Okay, so when x is 0, or when x is 2, y is 0. And so, so basically, I can do a picture of that. Okay, so we found our 0 to be 2 t equal to positive 2. We're not interested in here because we're not, time can't be negative. Okay, so now we're almost there. What we're going to need to do is evaluate our velocity function when t is 2. So coming back here, we'll look at v at 2 will be negative 32 times 2 minus 22. So v at 2 is negative 64 minus 22. So v at 2 is negative 86 feet per second. Alrighty. Okay. So now why don't we just get an overall picture of what's going on, and we'll plug in our original position function and check everything out. And I'm going to be doing it, in terms of x again. So here we go. So if we go to our y equals, and then our original one was negative, and then I'm going to go to insert. Oh, whoops. Okay, so y equals, so we'll have negative, insert, and it was what, 16, and then we had minus 22, and then this was plus 220. And then we're going to look at that derivative when x is x. And I'm going to adjust the window because we don't need to deal with any negative time. So let's just make this 0. So there's our original velocity function. The window, the window's not too fabulous. So, or that's our original position function. Okay. So let's go ahead, and we need to increase these y values. And actually, when you drop below the x-axis, you're going to be, it won't make sense, right? Because it'll hit the ground at the 0 of the function. So let's do that, and let's go up a little bit more and see what that looks like. And last but not least, we're going to go to our y equals, and we're going to turn on our derivative graph. I forgot to turn it on. And finally, we have this one, but our derivative graph is not showing. So let's see, let's get an idea of the values for our derivative graph. It should be showing up. We did that. For x is x. Oh, you know why? Because we need to have negative values for our derivative graph, right? So let's do this. Let's go to our window, and we will keep y. Forgot about that. For our derivative graph, we need that. So let's put y at, I don't know, negative 100 for the minimum and see what we get. Okay, almost there. We want, it would be nice to what I want to see is what happens when our graph hits the ground. So go back to window. Want to get the lower y value, a lower minimum y value. So I'm just going to try negative 200 to 200. There we go. Okay. So here's our graph, and I'm just kind of interested in just kind of examining what the zero of the function is, and then figuring out. And by the way, we're going beyond our problem right now, which is fine. I just want to scope out what's happening with all this stuff. So if we go to second calculate, 0, enter, and then we have left bound. Get it in here. Sorry, it went too far. Okay, that's good enough. And then right bound. A little more. Okay. All right. So basically the ball or whatever it was hits the ground at 3.08 seconds approximately. Okay. So here at 3.08, let's figure out what y would be, right? So for the second one. So here, do you see that when the ball hits the ground, the velocity is negative 100, 20.68 feet per second. So it's going pretty fast, right, by then. Okay, so let's just go ahead and make a copy of that so you have it in case you're interested. And I think that does it for today. And then, of course, for ours, we would change it to S and T. Okay. And right here, this represents the velocity. It's the ground. All right. Well, enough playing around. You guys are probably done. Okay. So have a great rest of your weekend, and I will talk to you soon. Bye.